Hello everyone, this is Alexey, and today we will be talking about a new tutorial. This will be a pretty kind of unusual tutorial in which I will show you some of the features of classical molecular mechanics and force fields in Libra, and the way you can mix different types of force fields and define different types of interactions with customized parameters and data types, parameters and atom types. I'll show a few demonstrations of how you can use this for different types of simulations. For instance, if you want to impose some certain geometry on your molecule, and so I've tried to record this tutorial in the morning, but then I realized that there were some kind of features I needed to kind of check in the code itself. So that's what I have been doing the entire day, and finally everything kind of has set up, and new updates are available in the Libra, and most importantly is my better understanding of this code. Okay, so we are here in this test Libra py directory, and here I created test 10 mix ff. Yeah, so that's for mixing of force fields. So you can see what is inside, and I also have it here. Yeah, so basically the script is here. So what happens here is we'll start with the standard thing. Create universe and load properties of elements, and then we create a force field. But then in this case, this force field object only has bond stretching term, which is just harmonic oscillator type of term. And of course, if you do dynamics like that, well, you will get some sort of floppy chain dynamics. Actually, yeah. So I haven't said what sort of system we can add it, and this is actually a chain of 10 hydrogen atoms. So let me basically show you what happens if you do this. And by the way, so here we have another. Uh, yeah, okay. Actually, before I will show you, so let me kind of describe what happens here in the script. So this is one force field kind of standard setup UFF, but then we also create another object also of the force field type, but then here we only define angle bending terms which we will vary, and we call this force field XFF, whatever it is. Now, in the following lines over here, we actually kind of manually define this force field. Basically, this is what happens in kind of hiddenly in this load UFF function. But in our case, we also so for instance in load UFF, we would only load atom records, so define atom types, and that's all you needed. But here we also define records of other types, for instance angle, like here. So and that's especially important for our test. Okay, I'll talk about this a little bit later. Now, what happens next is this, well, you will load the molecule and then determine functional groups, initialize fragments, and here we create a Hamiltonian object to be, some sort of atomistic molecular mechanics Hamiltonian, and then we set up all the interactions. We also showed the statistics, like how many interactions of different type we have created, and then we also show more details of these interactions. This is actually something new I have added today. And then here in this part of the script, this is actually where we will be adding the second force field, but I'll show you how that works later. And eventually we'll print out energy, and here we'll do dynamics, but we also will be cooling system periodically. So eventually, if you have this just cool, then it's basically optimization, some sort of annealing dynamics. Okay, so for right now, I'll just comment this line, and then so will be doing just dynamics, and then I also want to comment this section where we add the second force field, right? So for now, our Hamiltonian only contains a single force field of this UFF type with only bond like harmonic stretching terms. So, and then if we run this calculation here, basically, yeah, this one, that doesn't take a lot of time. 1, 2, 3. Okay, so that generates us this sort of energy file. You can see the total energy conserved. So this is molecular file, which I will load in VMD. So the dynamics will be something like that. So yeah, basically we start with this linear chain of hydrogen atoms, and then this is our dynamics, and you can notice that, well, this is like really floppy chain because we don't even have van der Waals interaction. So atoms can even overlap each other and yield this sort of strange dynamics. Okay, so that is what happens if you only have bond stretching term. Okay, now and this is of course dynamics, so I'll just remove this part. And also, if you look into the output, what happens here, well, you can see all the sort of definitions of functional groups, atom types, perception, and this is a statistics. So for now we have only 9 interactions, and these are all bond stretching interactions. Well, because you have 10 hydrogen atoms, that means you have 9 bonds between them, and these are 9 interactions you have. So this is the printout for the details of these interactions. For instance, interaction number 1, it is for the of the bond. So in interaction type 0 means bond stretching, and functional 0 is a harmonic potential, and this is like for atoms 1 and 2 connected, the equilibrium distance and force constant. So that's basically what we have in the output. And then next we will be so next what we are going to do, we can of course let's say now we want to uncomment this section, and this is where we will be adding the second force field. Now the second force field adds some angle functional, so the angle bending, and so to define this force field, we first define atom records. So well, what happens is we'll just create an object of some Python class, and then we define the class data members like that. So you don't have to define them when you define the class. You can define them when you actually use the instances of this class. So, and these are the special names like this one and this one, which are known by Libra. And when you have an object with these members, and when you pass it to the set function of the atom record object, then this fields, these members, data members will be basically converted into internal representation of this object. And then basically you get this atom record object which you can add to your XFF force field. So through this add atom record function. So you do this for one atom type, for another atom type, and then in a similar manner you create records for angle, so for triples of atoms, and then we basically add them. So we basically have HB or HB two types of angles, and then here we define the properties of this sort of interaction. Now that's what we are going to play with. Now, so what I'm going to do, so now we have defined this force field, and then when we call the function set interactions for atoms with this force field, the function will basically look for all angles, and then take the information from the XFF object to create interactions of this type, and then you will basically print out new updated statistics of interactions and their details, and then we can actually run this dynamics. So let's try to do this again now, and we'll see what happens. Okay, that goes pretty fast. So you can see now the energy is still conserving. That would be our trajectory. So let's unload the previous one and then load a new one. Make a nice representation. So now this is our chain of hydrogen atoms, and we can visualize the dynamics, so that what happens, you can see that, well, this chain is still flexible and kind of bends, but at least it looks like a sort of a chain, not as a random collection of atoms that can overlap each other. So that, which is kind of nice. Now, if you also look into this output, you can see that, well, we now have two outputs. First is before adding this XFF force field. This is our standard output we had from the previous run. But then, once we have set up a new interactions with this new force field, we will be printing statistics again, and now you can see that now we have 17 interactions, 9 bonds, but now also 8 angles, which is exactly what we want. And also we now print out all the kind of intermediate information about this sort of interactions. And if you look at the details of interactions, so now you, for instance, have this intertype 1, which is angle bending, and functional 1, which is some sort of Fourier type of functional, and then you can see the parameters for that particular type of interaction. Okay, so now what can we do next? We can play with different settings of these parameters. By the way, let me also kind of explain a little bit about what happens here. So when we, before we go, when we pass through this line where we set up interactions for atoms, meaning we define bonding and angle bending interactions and so on. In this function, we will automatically determine force field atom types for the force field which was used here, UFF. So that means and those atom types will be set in system here. So and then basically um, um, at this point when we run it here, the all atoms in system will already have some atom types, force field atom types assigned to them, and that's why we here when we define this new record, we use the atom types from the previous force field UFF. It is probably possible to use any other atom types like arbitrary types, but I haven't tried this yet. So I think then one would need to define atom FF types here, similar to what we do in this script. And actually, let me explain what happens here. Now, when we define the atom type, we also define the connectivity. That means like how many or coordination of atoms. I mean how many like some sort of geometry that atom should have, and by default that coordination is equal to 2. But if we want some sort of linear like 180 degrees angle in each hydrogen center in our system, we will have to change this atom coordination to something else, number 1 in this case. And once we have changed this coordination, when we run this set interaction for atoms function again, then those new interactions will be set appropriately. Actually, I haven't deleted this file yet, so and you can see actually here if you look at this, so that's a property of one of the interactions of angle bending type. So, and it shows coordination is equal to 1. That's exactly what we want. Now, also so here you also have this sort of uh, print out, and it says like force field name is not defined, and then but this allows you to manually define any atom type. That actually comes from the line where we do this set interaction for atoms, but for the second time from this line, because at this point the force field XFF does not have any name assigned to it. So and that means when we check for existence of these atom types in this XFF field, there are no such rules to check, and that's why it kind of complains. But this is actually a convenient thing because now when we use this option, this function here, we already have the force field atom types assigned to all atoms, and then those numbers are used to determine interactions here. Okay, that's basically what happens here, and you can see that it happens when it first complains and then says, okay, atom 0 type is defined manually and it's H underscore. So that is actually a result from the previous atom type assignment. Okay, so I have explained the hardest part now. Now we have time for a little bit more fun and playing with this sort of parameters. So, okay, before right now, so first let me change my molecular dynamics to just optimization. So that's why I uncomment the system call, and that basically converts my MT to some sort of optimization code. Now, now then, I want to change my angle functional to harmonic. Harmonic. That's very simple type of functional. Actually, if you want to know what happens in there, you can find everything in source port. That's where all these functionals are defined. So this is like angle harmonic. It's theta ijk minus equilibrium theta squared. So that's basically um, what this functional is. So we change it to this sort of functional, and then we can play with, so we will just keep this angle force constant fixed, but then we'll change the numbers here. So let's try 90 degrees. So okay, and then yeah, and then we can just run this sort of calculations. Okay, unload the previous result. You can actually look at energy. So this is what happens. This is your total energy, and you can see it. Initially it's large, and then eventually it goes to very small number. That's what we want, right? And that's basic optimization. Now we'll load everything to VMD, change to a nice representation, and we can look at it. So this is what we get. Whoops. So, I mean, let me just show you how that happened. So we started with linear chain, and then eventually, well, that's actually pretty much fast at some point, and it loses kinetic energy, so it kind of slows down, and then eventually you get this sort of structure. And then if you look closely, every angle here is a right angle. So here 1 2 3 90 degrees, 1 2 3 90 degrees, 1 2 3 90 degrees, all angles are 90 degrees. So that's exactly what we want, and that's where this sort of manipulation is convenient. Now let's say we can change this number to, we want to change it to 120 and see what happens then. Okay, run calculations again. Now then do this stuff again. So delete molecule. By the way, let's look at the energy. Yeah, energy now also decreases. And then we load it here. Change to nice representation. Look at this. And this is what we have now. We have this sort of structure. Oops. And then every angle is 120 degrees. Here, here, and then this one, and this one. So that's the structure we get with this sort of setting. Um, Now we'll delete this. Let's try some unreasonable sort of setting for harmonic oscillator. 180. So that's actually a problematic angle because you will get singularities when computing forces for such an equilibrium angle. And well, maybe that will work, I don't know, but I would not recommend using this setting for your dynamics. But let's see what happens. So it somehow converged to some small energy, and maybe even we get some sort of linear structure. We'll see. So Oh, that's interesting. So, I mean, yeah, you do get some sort of linear structure, but probably the forces may have some sort of errors, so better not use harmonic potential for linear chains. And instead of that, we will basically be using another type of functional, and that was the one we started with, harmonic, oh, not harmonic, Fourier. For, for, yeah, Fourier. Okay, so that's basically, again, if you want to know what it is, go into this file, and this is where it is defined, angle Fourier. Um, this is the functional that will be called, and here it's a trick. So depending on the coordination of your central atom in this angle, in each angle, you different kind of versions of this function will be called. If it's one linear, three or four trigonal, tetragonal coordination, then we'll call some special one. If it's two or whatever else, a general one. So let's look at, and what is important. So if you look at this general, the parameters may not even depend on equilibrium. Well, for general, yes, but for special, the parameters do not depend on equilibrium theta, only on n. So here, let's do this. We change it to Fourier, and our coordination is still 1. Oops, not here, but here, right? And then we'll just keep the equilibrium theta to be 180, and I will just run this sort of calculation. Okay, now here's your energy optimization, and the structure will be this. You still get the some sort of linear structure. But then let's look at what happens if you change the equilibrium angle here, 190 degrees. We still linear coordination, and then we run the calculations again. Energy converges, but let's look at the structure. Change it. Oops. Actually, I should unload the previous one first, and then load the structure, change to the nice representation, and I can show you it is still linear, right? So that basically emphasizes that if you use Fourier functional, then it doesn't matter which equilibrium angle you use. It's only depends on the coordination. But for certain coordination, then then there will be a dependence um, on the equilibrium angle. Alright, so I think I have covered most of the kind of topics I wanted to cover today in this tutorial. Let me know if you have more questions, and I hope you enjoyed this sort of video, uh, and now you will know how to mix different force fields and different types of interactions in your model.